In this video, we're going to talk about acids, bases and buffers, ionic product of water. This is how you calculate the pH of strong bases. And in this course, you don't do the pHs of weak bases, just strong bases, okay? So this is a number, and the number is in your data sheet. So you don't have to remember it. But we'll talk about that in a second. pH strong bases, you can see here is the pH scale in terms of universal indicator, okay? And pH of strong bases, they're usually proton acceptors, and we still measure their hydrogen ion concentration to determine their pH. Okay, so we look at their hydrogen ion concentration to determine their pH, even though these tend to be alkalis and things like that, which means you normally think of OH minus concentration instead. But we look at the hydrogen ion concentration of these strong bases. The concentration of hydrogen ions in the solution varies between the two following ones. So that's pH 7 and that's pH 14. Let's look at this on the actual scale itself. So there's the scale. You can see, again, really important to notice, we've got a -1 there. Okay, and you may have seen that in an earlier film. Let's twist that up. We're just looking at that area there. Okay, we're only looking at that area there, and that is it. Let's go from pH 7 to pH 14. Remember, that number is the hydrogen ion concentration, and the power you raise it to, if it's -7, just means that pH is 7. If it's -14, and so on, 8, 9, 10, 11, 12. Now, if that's the case, we're assuming that they're fully dissociated proton acceptors, so fully dissociated. And that means that you're only going to get ones like this, hydroxides. And you might get slightly more complicated ones like this. Okay, but strong bases in the ionic product of water, how do we connect them? So the ionic product of water, which is in your data sheet, so please never worry about forgetting it, is this number here, and it is at very important standard conditions. So standard conditions is 25 degrees Celsius, for example, 1 mole per decimeter cubed, okay, and 100,000 pascals or 100 kilopascals. But the important thing is this is the temperature, and we'll talk about the temperature later on, but this is 25 degrees. So at 25 degrees, it's this number. Now, if that is the case, put that to the side. And we're going to do some example questions. So first example is with sodium hydroxide, the simplest one. Now you can really overcomplicate this. I'm going to keep this as simple as possible. Okay, what you have here, 1 mole per decimeter cubed, if you had 1 mole per decimeter cubed, it would fully dissociate, which means you would get 1 mole per decimeter cubed of that and 1 mole per decimeter cubed of that. It's a 1 to 1 to 1 ratio, and you'd have nothing left here, okay, because it would all fully dissociate. So you can assume that the important thing is you can assume that the concentration of the OH minus ions is the same as the original NaOH. So if we then go to the actual Kw expression, the Kw expression is here, it's H plus times OH minus. I could go into how you derive that and everything like that, and you could look at that in other videos and things like that, but you really don't need it to use it. So just need to remember Kw equals H plus OH times OH minus. Now we already know if it's a strong base, we can know what the OH minus is. And we know what the Kw is because at 25 degrees, it is that number. Okay, so if we put a question up, 0.1 mole per decimeter cubed sodium hydroxide. Okay, so we're going to do that. And remember, it's fully dissociated. So if, for example, if we start off with 1, we go 1 and 1. But we're not starting off with 1. Okay, we're starting off with 0.1. Okay, which means we'll have 0.1 of that and 0.1 of that. So that's the case. We know what Kw is. So Kw is 1 times 10 to the minus 14. Got it from over here. Okay, and we're going to divide by the OH minus to get the H plus. So just bring that down. We know the OH minus is 0.1. So we will go 0.1. And that will equal our H plus concentration. Now our H plus concentration is going to be equal, and so if we do that, to 1 times 10 to the minus 13. Okay, so we've got 1 times 10 to the minus 13. That's our concentration of our H plus ions. And then all we have to do is, let's get a different colour, okay, is say, right, okay, our pH, because that's the point, I want to calculate the pH of this solution, okay, is minus log, and it is 1 times 10 to the minus 13, which handily for us is 13.00. Notice 2 zeros, 2 decimal places every time. Okay, and that is how you do the simplest of KW questions. So our next question is going to be about magnesium hydroxide. And magnesium hydroxide, we're just going to use the same concentration here. And you say double the amount because the ratio is 1 to 2. Now that means we're going to have that much in terms of our concentration with this question. So 0.1 mole per decimeter cubed of aqueous magnesium hydroxide. Again, just do it yourself. Okay, so let's get out of the way and we can do our question. Okay, so again, we've got 1 times 10 to the minus 14. We will divide it by the OH because we're bringing it down there. The OH is 0.2. Okay, because the OH is 0.2, that equals 5 times 10 to the minus 14. So 5 times 10 to the minus 14. So we've got, and that is equal to our H plus concentration. So we've got our H plus concentration, and then what we can do is we can go down here and we can just go, right, pH equals minus log of our H plus. Our H plus is 5 times 10 to the minus 14. Okay, and if that is the case, you put that into your calculator and you should get 13.3 to 2 decimal places. Okay, and you can see with the same concentration how we're getting a different pH. So we've gone from sodium hydroxide to calcium hydroxide up to aluminium hydroxide now. So we can see the ratio is 1 to 3. So we start off with 0.1 again, but we go to 0.3 because the ratio is 1 to 3. So my hydroxide concentration is 3 times that of the original because of the ratio here. Okay, you can see there's 3 OHs per molecule of aluminium hydroxide. Okay, so if that is the case, again, we can do it quickly. Okay, so 1 times 10 to the minus 14. We are going to divide that by our OH minus. We know our OH minus is 0.3. Okay, so we know that is 0.3. And because we know that is 0.3, we know that is going to be equal to our H plus concentration. Our H plus concentration is going to be 3.33 times 10 to the minus 14. Okay, so we've got that. That's our H plus. And all again we do is we take it down here and we go pH is equal to minus log, and that is 3.33 times 10 to the minus 14. Okay, and then basically all we do is go equals, let's get a different colour. Okay, and that would be 13.48. And again, 2dP. Okay, so again, hopefully by the end of these 3 ones, you'd be comfortable with calculating the pH of any number of different bases. Our next one is trying to find out what the concentration is of the original base. So we've got calcium hydroxide here, and let's put the question in front of you. Calculate the concentration of the calcium hydroxide that has a pH of 13.5. Now, I've said this many times and I'll say it again. If you're given a pH, the first thing you do with it is get a H plus from that. Okay, let's put it to the side and highlight the key parts. Okay, so we've got concentrations of calcium hydroxide, pH of 13.5. Now, 13.5 needs to be converted to H plus, and we can use this equation. That's why I brought that down. Okay, so we can use that equation to convert it into H plus. And then we can rearrange this to get our OH minus. Now, really important thing to notice is that there is a 2 to 1 ratio. So 2 to 1 ratio. So this concentration of OH minus is going to have to be halved to give the concentration of the original. Okay, so it's going to have to be halved. But let's get to that in a second. Okay, so if we look into H plus, we want to go H plus equals 10 to the minus, and our pH is 13.5. Okay, so our pH is 13.5. That will equal a H plus of 3.16 times 10. Let me get that right here. 10 to the minus 14. And again, carry on, stop the video, do this if you can. We then have to rearrange this equation. So we've got the H plus and we've got the Kw. So 1 times 10 to the minus 14. So if we then go 1 times 10 to the minus 14, which is our Kw, and then we divide by the H plus, sorry. So divide by the H plus is there. Okay, and H plus is 3.16. Now I'm putting 3.16 times 10 to the minus 14, but 3.16 is the number in the calculator. So remember the number in the calculator, don't just round it. No rounding until you get to the final answer. Now if that's the case, that will equal our OH minus. Our OH minus, okay, is going to be 0.316. And again, in the calculator, okay, so that is equal to our concentration of OH minus. Okay, so our concentration of OH minus is done. That's the concentration here. The original question asked for the concentration of the calcium hydroxide, which is this one. Ratio is 2 to 1. So we take our 0.316 and we divide that by 2. We're going from here to here. Okay, that will end up in a rounded value. So I'm rounding now because it's the final value of 0.16. Okay, and that's 0.16, and that's our final concentration in moles per decimeter cubed. Okay, and that is of our, see if I've got the space here, that's our calcium hydroxide, so our calcium hydroxide, and our final answer. And that is how you get the concentration of a base from your pH in a question. So in this question, we're going to work out the pH, and the question is down here, the pH of a solution of sodium oxide, okay, gives you a mass in excess water, which is 1 decimeter cubed. Nice, giving you the 1. Okay, and then gives you, and then here is the equation. Now, might not give you the equation, so you need to know that an oxide dissolved in water creates a hydroxide, and the ratio is 1 to 2. So 1 sodium oxide to 2 sodium hydroxides. So if I calculate the moles of the sodium hydroxide and then times it by 2, I can get the moles of, I calculate the moles of the sodium oxide and then times it by 2, I can get the moles of the sodium hydroxide. So if that is the case, that's why I've put this ratio 1 to 2 here. So what I've done already is I've done my number of moles. I've taken my mass, 1.55 times 10 to the minus 3, divided by the molecular mass, and this is our equation up here. Okay, and I know the ratio is 1 to 2 from my equation. Now that means this is the number of moles of Na2O. Okay, so I need to times that by 2. Now that number times by 2 is going to be 5 times 10 to the minus 5. So that means I've got my number of moles. That is my moles, let's call that N, of sodium hydroxide. Okay, so that's our number of moles there. So we've got our number of moles. Now from there, we need to use do it as a concentration, because the question says calculate the pH, and we always calculate pHs with concentrations. Okay, so we need to turn that into a concentration. Now the really nice thing is this is 1 decimeter. So if you want to do the concentration is going to be moles over volume, as we've got here, moles over volume. Okay, and that moles over volume is 5 times 10 to the minus 5, okay, over the volume, which is 1, which means our concentration is 5 times 10 to the minus 5. Okay, let's do the units as we've got the space. Okay, that's mole per decimeter cubed. Right, from that point, we have got the concentration of the sodium hydroxide, and we know in the sodium hydroxide, if it's fully dissociated, if that's the concentration of our sodium hydroxide, the sodium hydroxide will be equal to the concentration of the OH minus, okay? Because it's fully dissociated. The sodium hydroxide fully dissociates. So if you've got 1 mole of sodium hydroxide, you will have 1 mole of OH minus, which means this number right here is our number of moles of OH minus. Okay, so we've got the number of moles of OH minus, which means we can now start using Kw, because Kw divided by the concentration of OH minus is H plus. So we can put that in and we can say, right, okay, Kw is 1 times 10 to the minus 14. You will divide Kw 1 times 10 to the minus 14 by the OH minus. The OH minus is 5 times 10 to the minus 5, which will then, remember, equal your H plus, which if we put it in a calculator, hopefully, that will be 2 times 10 to the minus 10. Remember, keep the number in your calculator. Okay, so make sure you keep that number in your calculator. It's nice. So we've got that as 2 times 10 to the minus 10. Okay, and now all we have to do is we have to put it into our pH equation. So our pH equation is pH equals minus log, and we put 2 times 10 to the minus 10. Okay, and that will equal a pH of 9.70. 2 dP again. Okay. Right, and that is how, from a metal oxide, you can get a pH using your knowledge of knowing that when it dissolves in water it creates sodium hydroxide. A little bit more complicated, and one definitely you need to know if you're going for the really high grades. So I'm going to finish off with 2 tricky questions on standard conditions and the ionic product of water, one which most people will miss. Kw is determined at standard conditions. The standard conditions 298 K, 25 degrees Celsius, 100 kilopascals, 1 mole per decimeter cubed. And you get that number. But that doesn't mean Kw always has to be these values. It can change. And for 95%, 99% of your questions, it's going to be this. But there may come a time where they change the temperature, and temperature changes constants. So that's what we're going to go over now. So Kw has been determined at 323 K, which means the temperature's gone up, and found to be 1 times 10 to the minus 10, which means that Kw's gone up. Is the enthalpy change endothermic or exothermic for the equilibrium underneath? Okay, so here is your Kw equilibrium, okay, and you've got H2O going to H plus and OH minus. Now just have a think about that, stop the video and have a think about it before I explain. So if I put that up to the side, first of all, it is endothermic. I'm going to explain why it's endothermic. A simple way of thinking of it, you're breaking bonds. To break bonds, you have to put energy in, so therefore it's got to be an endothermic reaction, okay? However, this question wants you to use the data to explain it, so you've got to do more than that. You can't just say it's endothermic. So if that's the case, let's look at the temperatures here and look at what's happening. So that's increasing, Kw is increasing, and temperature is increasing, right? So that's increasing as Kw is increasing. Now, Kw is this expression, which means that Kw will get bigger if these numbers are bigger, which means those numbers must be increasing. That means that the equilibrium must be going over to the right, and more of this is being produced. So as the temperature is increasing, the equilibrium must have gone to the right, okay? And if you're increasing the temperature, according to Le Chatelier's principle says that you do the opposite. So if I'm increasing the temperature, the system will want to follow the reaction that lowers the temperature. The one that lowers the temperature is the endothermic reaction. But this is exactly what you need to write in the exam. But this is about Le Chatelier's principle. Remember, if you heat something up, it wants to lower it, and it will lower it by following the endothermic reaction. Okay, and that's your 3 answers for this question. Remember, if you're given the data, given it in the question, you've got to use it. A tricky question. Next one is neutralization in the ionic product of water. Is the water at 323 K neutral? You know it is at 25 degrees Celsius. You're told all the time that it is. But we've increased the temperature. Is it neutral at this point? Okay, so we know from our previous, that the Kw went up. Okay, we know Kw went up, but the important thing is this, okay? Every single time a water dissociates, it goes into one of these and one of these. That means it doesn't matter if the equilibrium is over to the right, your concentration of H plus will always equal your concentration of OH minus, which means it doesn't matter how the kW changes, because the concentration of H plus will always equal the concentration of OH minus. That means it will always be neutral, because that is the definition of neutral, your H plus equaling your OH minus. Okay, and that is all of the questions on kW that you will come across.